Hi, I am Bizerra and I will be presenting the paper entitled A Solution for Fast Parallel Storing Managing and Accessing Seismic Data. This work has João Speglis and Murilo Borato as co-authors. Seismic data processing requires a huge amount of geologic information that are stored most of times in SegWit format, the industry standard. This format was developed for tape storage and is incompatible with today's high-performance computing standards. Thus, the main goal here is to convert data stored in this format to one that is focused on performance. To better understand the trivial solution, let's take a look at the organization of a file in the SegWit format. First, we have a global header, with metadata referring to the entire file. And this global header is followed by double header samples referring to each trace present in the file. These traces contain geologic information for each recorded position, and all of this is stored in a sequential manner. Therefore, a trivial solution to group traces that have specific positions in common, e.g. source position, starts from the first trace header and goes to the last trace sequentially. Then, after identifying the traces that have the selected key in common, they are extracted from the file and grouped together. This trivial solution has some pros and cons. As pros, implementation requires no effort, and no extra disk memory is required. As cons, all data headers must be read at least once, all computational effort is not persisted, extremely large data may not fit in RAM, reading in parallel is compromised with the parallelism of shots. So, in this work, we propose a solution as follows. Our solution is divided into the conversion of SegWit data to an HPC-compatible format, data persistent, and the manipulation of this new format. And here become our specific goals. Convert and persist imported SegWit data, allow handle and parallel access, fast trace gather reading and writing, support the addition of multiple computational resources. The conversion process works as follows. SegWit file data is divided into smaller parts, and these parts are processed into DAS data frames, a lazy structure that keeps a graph of all the operations to be computed. Then, a compute node can iterate over parts in order to persist them. The use of tasks in our solution allows the addition of multiple computational resources to do this task. Using single or multiple nodes, the task ends with data persistence to file. The file format chosen for data persistence was Parquet. Developed by Apache to optimize work with complex data in bulk, this columnar format allows you to read only the columns you need, which significantly improves I/O operations. In addition, Parquet is optimized for queries that process large amounts of data without copying information to RAM, and allows data compression for a variety of encoding schemes. Thus, all data that was previously converted from SegWit to DAS data frames was persisted to disk in Parquet partitions. In this way, the reading and writing process of our solution work as follows. The write, top-down, starts from a DAS data frame and persists it in Parquet using PyArrow engine, also from Apache. The read, bottom-top, on the other hand, do the opposite process, joining the partition present on disk and generating a data frame. The performance analysis were done from two perspectives: conversion from SegWit to Parquet and data gathering from specific trace positions. In the conversion process, we got a 10 times speedup using a 40 GB synthetic file. The process that lasts almost 800 seconds can be done in about 80 seconds using our tool. Using the real weekend grabbing data of about 1 GB, our solution was capable of gaining about 8 seconds, from 12 to 4 seconds. This represents a 2.73 times speedup. In the gathering process, we got a 3.99 times speedup using the 40 GB synthetic file. This is a 28 seconds gain, from 37 to 9 seconds. The gathering using Viking gravity results in a 0.1 times slowdown. This slowdown was caused by Viking gravity file size, once the major part of Parquet and Dask optimizations was designed for a large amount of data. The loss in this case was smaller than 1 second. We also use a 2 TB synthetic file to test gathering, and it results in a 9.2 times speedup. This was a game changer. Here we achieved a gain of 26 minutes, from 28 to 2 minutes. And that's all. Thank you for your attention. For any doubts, send an email and we will respond to you.